Greetings, I'm Yvonne, staff for Science for the Public, and I welcome you to Contemporary Science Issues and Innovations. As you know, the climate change crisis is directly tied to the excess accumulation of carbon dioxide in the atmosphere, largely the result of fossil fuels. Even if we could switch to 100% renewable energy today, we must somehow remove trillions of tons of excess CO2 from the atmosphere. Our guest today will explain that situation and especially the carbon capture and conversion system that he and his colleagues have developed. Dr. Sami is assistant professor in the School of Sustainable Engineering at Simon Fraser University in Vancouver, Canada, where he leads a team focused on engineered interfaces for sustainable energy. Although Dr. Khan is still early in his academic career, he's already received several prestigious awards for his innovative work. One of his projects that has attracted considerable attention involves carbon capture and conversion. Today, he'll give us the background on the CO2 crisis and the major approaches to CO2 removal from the atmosphere, and he'll describe the carbon capture and conversion system he and his team have developed. He'll also talk a bit about some other exciting projects his lab is working on. We are very pleased to welcome Dr. Sami Khan. Thanks so much for joining us today from Vancouver.
Thank you so much. I appreciate the very kind introduction and warm good morning wishes from Vancouver. This is actually the view from our beautiful campus at Simon Fraser University.
Oh my.
And it's just a pleasure connecting from here.
I'm so glad you're able to connect with us today. Dr. Khan, I'd like to start off with some background about the excess CO2 in the atmosphere and how that relates to climate change.
Yeah, absolutely. So, all gases are made of fundamental small particles that are called molecules. And these molecules are fascinating. If they are poked around, they spin around. If they're given some energy, they dance, they rotate. So these fundamental properties of these molecules dictate how these bigger challenges like global warming is happening. So on one end, you have molecules like oxygen and nitrogen. When the rays of the sun hit the planet's surface, there's some of the heat there that is reflected back. Now, oxygen and nitrogen molecules, they let this heat pass through, and there's some level of dancing and rotation that happens with them, but it's not very significant. But on the other hand, you have these gases that are called greenhouse gases, like CO2, where when this radiation strikes the CO2, it absorbs this, and then it starts to dance around, it starts to rotate and vibrate, and then it emits some of this absorbed radiation back to the surface of the planet. So this is kind of like an insulating blanket, if you think about it. And this is the fundamental reason why CO2 on a very physical and chemical level is causing global warming. And when the planet was created, this was part of the design that there are greenhouse gases to have a steady level of temperature on the planet so that it can sustain life, it can sustain everyday activities. But that's where now when the system is disturbed and there's an excess of these molecules, then it can start to lead to more heating.
Right. And another thing is that there is sometimes a misconception that if we just could switch over to renewable energy right now, we'd be okay. But that business of how CO2 in particular, compared to say methane, hangs in that atmosphere and continues this heating and really causes a problem. Is that the case? It doesn't go away.
Yeah, absolutely. Because if you think about it, the atmosphere is all the gas volume that is surrounding the planet. If we keep adding gas to the atmosphere, it is just going to keep increasing the thickness of the atmosphere. It is not going to escape out of the space. So
Right.
there has to be somewhere else where the CO2 has to go to in order to regulate the levels that are optimum for the temperature of the planet.
Right. Thank you. Everybody knows at this point that you have to switch to renewable energy. That's not the issue here. It is, what are we going to do with that excess? So that's why I ask you to make sure we can understand that even if we switch immediately, we're still going to have this excess, and that we're not talking about for a few weeks, that this is going to be probably centuries of this, and it's causing enormous damage. Okay, then there are all these various methods, everything from solar geoengineering to capture and sequestration and all these things. Could you please tell us a few major ideas in your mind? What are a few major methods
Yeah, absolutely. So you
proposed, the ones
mentioned
that are, yeah.
geosequestration. So the idea there is that CO2 is converted into a high pressure liquid and then pumped underground where it can be safely stored in rocks and geological reservoirs, and then kind of be locked away in a prison out there for many, many centuries. Now, this
Yes,
is, this sounds fancy. This sounds like this is a great approach to, trap the CO2 and put it somewhere.
just dig a
But,
hole, yeah.
there are challenges here.
Yes, so I understand. Can you tell us any of those problems, maybe with sequestration?
Yeah, so this is where I would like to do more of a relative comparison to conversion technologies,
Yes,
because CO2 is a very stable molecule. It is the most oxidized state of carbon, so it persists in the atmosphere. It is not very reactive. So, but there have been now advances to convert this very unreactive molecule into useful products. And by useful products, I mean products like cement or carbonate, where these are now solids that contain CO2 in a solid form, but they have a useful need in society, either as building blocks for construction or polymers, which are needed now for everyday objects. So compared to this, where CO2 is captured and converted to something useful, there's a disadvantage with geological storage because it's still the CO2, and then it is in a higher pressure form, which arguably there are some challenges with that in terms of environmental impact. And as you mentioned, drilling holes, which requires again a very specific recipe and very specific confidence level that this would stay stable. It would withstand earthquakes. It would withstand any kind of catastrophic event where the CO2 would not leak out and then cause a higher concentration suddenly in the atmosphere.
yes.
So that's why I would like to think of this as a relative approach compared to other approaches that have
Yes.
a better set of advantages.
Okay, so the big problem with the sequestration is that it's very problematic in terms of whether it will stay stored underground.
I go back to the disadvantage about the conversion, because the CO2 now has been just taken from one physical form, which is a gas, now converted to a liquid form, which does not have any use or end advantage where it could be utilized for societal needs. So that's where relatively that challenge comes in.
Most of the time we hear either about solar geoengineering or about carbon capture and sequestration. We hear a lot less about methods of carbon capture and conversion. And so I wonder if you would tell us about that, about what you're doing and what's the difference there?
Yeah, absolutely. So here now you add another letter to the acronym of carbon capture and storage. So there's various ways of doing that. You can add a U between the capture and storage and call it utilization. or you can do carbon capture and conversion. So those are 3 Cs. And both these words point to the idea that the CO2 that is captured can be used for a valuable, as a valuable product, or in any product that's converted to. And this is very much inspired by nature. So plants do this every day when they photosynthetically convert CO2. So they're not just capturing the CO2, but now they're generating glucose and sugars that they use to run their to provide the energy for their daily routine. But also, that's where food comes from. So this is where they're synthesizing food. So there's a big advantage to not just capture CO2, but then think about where this can be used and if it can be converted to valuable products.
Okay, so that's you there. Could you please tell us about the system that you and your colleagues developed because you converted into something else? So could you tell us what it is that you do with the carbon capture and conversion?
Yeah, absolutely. And I think here, before I describe this, it's important to talk about challenges in converting the CO2. So one of the main challenges, as I mentioned, is CO2 is very stable. So when I'm talking about stability, I'm looking relative to, let's say, cooking gas, where if you spark the gas, it's it's burning right away. So there is a chemical reaction that is spontaneous and happening. That is harder to do with CO2 because it's already in a very oxidized state. So anytime we're looking at conversion of the CO2, we have to realize that the CO2 has limited reactivity because it wants to be very stable. It wants to be, in the state that it is. So that's where now we have to turn into what do we do to make it more reactive. So that's where there are library of options like catalysts. So specifically catalysts, the role they play is that they reduce the energy barrier of reaction. So they get reactants together on the surface and then convert it into a product. But then also at the same time, you might have noticed that if when you're drinking soda or Coke, when you open the bottle, immediately CO2 bubbles start to come out. And that's because that CO2 is under pressure in the water. So that way now it is able to dissolve and stay in that water. But if you let the CO2 escape out, if you keep the lid open for a long time, then you know that the CO2 escapes out. So there's only so much that CO2 can dissolve in water. So there's like a limitation to how much water can control it. And this is a challenge because water containing CO2 is reactive. So CO2 is acidic in nature. So whenever you dissolve it in water, there's this experiment that you can do where you could put a tooth in a soda bottle and then close it. And then, 1 week later, the tooth dissolves. And that's because the CO2 in the water is acidic. And I don't recommend this at home, but just if you have, especially children, if the milk teeth are falling off. Yeah, so that's now a hint to us that CO2, which as I described is not very reactive, can become reactive if it is dissolved in water. So that's now where this technology and these advances here in CO2 capture and conversion are coming, where we realized that could we capture CO2 and convert it into a reactive form? And one of the methods to do that is to dissolve it in a liquid solution that will be very perceptive and very receptive to dissolving CO2. So this is where the fundamental motivation for our technology came from, that in order to convert the CO2, how can we convert it into a useful form and capture and hold it there? So just wanted to give a bit of context as to what the challenges are.
Right, but then you did it. And so first of all, before you show us how it works, because apparently there are real challenges with that technology, but you seem to have overcome them. And that was one of the reasons why your project got so much attention. But what would you convert it into? for example, if we could get that first, what can it convert into?
Yeah, that's a great question. So the reaction here, it's called a reduction reaction, where CO2, it's in an oxidized state and it's getting into a less oxidized state. So those less oxidized states are typically hydrocarbons, which are methane, carbon monoxide. So carbon monoxide is not a hydrocarbon, but in that same category of a reduced state. But hydrocarbons like methane, ethylene, ethane, and then liquids like ethanol and propanol. Now, all of these are very useful because methane is useful as a fuel to cook or to run engines. And then ethanol and propanol are liquid fuels. So these are easier to store and they have a high energy density relative to gases. But then also ethylene is a very attractive product because this molecule is the precursor that is used to make polymers. So you might have heard of polyethylene bags. They come from this small molecule, ethylene, which is originally a gas, but through a polymerization reaction, it becomes into a polymer bag like polyethylene, which now you can use for various applications. Now, a lot of these, typically, as you mentioned, used to come from the fossil fuel industry because that's where there's a rich source of hydrocarbons and oils that are now useful to make polymers, useful to make pharmaceuticals. But now through this approach with direct conversion of CO2 to these molecules, we can have an alternative chain to make these valuable products.
And these are like non-polluting?
Well, so that's an interesting question because plastics, plastics are they have a impact, and but there is there have been studies on where it is possible to use polymers in day-to-day applications, but then have a reasonable recycling and closing the loop process where they can still be used, but then have a reasonable end of life. But then also at the same time, pharmaceuticals, so medicines that we use every day, these require some fundamental chemicals in order to make the structure. And today, most of these chemicals come from the oil and gas industry because that's like the rich reservoir of these materials. So by having this alternative manufacturing process where CO2 is converted to these valuable chemicals, then there can be an alternative pathway to make medicines, to make polymers, a lot of valuable products, and therefore also in a way reduce the reliance on the oil and gas industry.
I see. Now, so there is a product, and that will probably open up a host of other innovations as you step along there, but you can say at this time, we can convert this stuff to something useful. Is that 100% of it, or are we talking about 2% of in this conversion?
That's a great question. And that's exactly where selectivity is a challenge in this process. Because when you're dissolving CO2 in water, and if you are using this medium for conversion, then you not only have CO2, but you also have water molecules. And the approach that we studied is called electrochemical conversion, where the idea is that an electric current is fast and it is causing a conversion of CO2 on the surface of a electrocatalyst. But if that electrocatalyst is also exposed to water, then it is also possible that the water can react and generate hydrogen. Now, this is not bad because hydrogen, as you know, is very useful. Absolutely. But as you mentioned, this is where now a selectivity challenge comes in, where in this soup that you have, you not only have CO2, but you have other reactants, and you might have an issue where the CO2 is not getting converted, and all of this electric current is going to convert something else that you don't need.
Right. Well, but that's something that is addressed at some point. But you got a lot of attention because your particular system was able to do a significantly better conversion there, I believe. And so there is a little video clip to show it. But for most of us, we don't understand what's going on. Could you by any chance show us that or tell us how that works? Because you just talked through it a little bit there, but can you do it in English that we can't?
Absolutely, yeah. I'm happy to. And before I show the video, a bit of a context that our intention is to increase the concentration of CO2. So as I mentioned, the challenge is that if you have a soup that has two ingredients and only one of those ingredients you want to convert, then a rational approach is, can you increase the concentration of that ingredient? So you can think of it as a soup analogy. If you want it to be more spicy and you like spicy food, then you would want to increase the concentration of that. So the same approach applies here, that we wanted to think, how is this CO2 introduced into water and how can we enhance or increase the amount of CO2 that is present in a given volume of the liquid, which is basically the concentration. So this is where we designed a nanotextured, a micro-engineered surface where it is able to capture CO2 within the texture. So a good analogy I can give here is like, it's a paper towel. So, you use paper towels to soak up drops of water. And then when you soak it up, then the paper towel facilitates a quick evaporation of the water. So now the same thing, but in reverse, where now this paper towel is selectively capturing CO2 bubbles in a liquid. But then because the CO2 is captured and held there, it is now able to dissolve faster and get into the liquid faster. So this is where these videos will demonstrate that concept. So I'm just gonna quickly share my screen. So this video that I'm about to show is, typically how CO2 is introduced into a liquid. It is introduced as bubbles. So when bubbles come into the water, if you're bubbling throughout, then you hope that it would dissolve. But this is a high-speed camera video where the CO2 bubble is coming. And you can see that when it strikes the surface here, it gets captured very quickly into that surface on that top. So that surface on the top is the paper towel that I was describing. So the bubbles now are coming and getting captured and then spread as a very thin layer. So now this is in contrast to everyday regular systems where essentially bubbles are not able to get captured because everyday materials around us, they are not able to. So when these bubbles come and interact on everyday surfaces, so like, when you put them in a soda can or glass, then the bubbles typically go and they touch the surface and they bounce off. So this is not very efficient because there's no way to hold the bubbles. So when there's concentration of CO2 to come into the liquid, the bubbles are just going there and then they're escaping. So in contrast to this, what I showed earlier is that our surface is now capturing and holding the bubble there. So that way now it is able to enhance how much CO2 can get into the liquid. And this is where we have a color video to show that this actually makes a difference.
Yes,
so
that's the one.
Yeah, so let me just bring that up real quick. So in this experiment, what we're doing, and I'm just going to reduce this so you can see clearly, we're introducing a color indicator that will tell us how much CO2 is present in the solution. So this is a typical approach. So every day, when CO2 is introduced into a liquid, it is typically bubbled. So you can see that when it is bubbled, then the bubbles, as I showed earlier, they're escaping very quickly. They're not staying in place. So you can see that the entire solution here appears blue because that is the limiting concentration. That's just how much CO2 the solution can hold. But now, in contrast, if you see this other video where we introduce the CO2 on this particular trap that we developed. So on here on the left here, there is the paper towel that I mentioned. Yeah. So now the CO2 is directly being introduced into that paper towel. And you can see that, actually, I'll ask you, so when you see this video, Can you
Yes.
see a color change, a difference in
Yes.
color?
Yes. Yes.
So
Yes.
you can notice that I'm just going to pause the video here. You'll see that it is greener in this
Yes.
region and bluer in that region,
Yes.
which means that if the color is greener, it means that there's more CO2 in the solution. So by
Okay.
using this kind of approach, we have locally enhanced how much CO2 can get into the solution. And this is again going back to the soup example where now you have more ingredients. Now you're able to selectively convert that ingredient or have more satisfaction by having that ingredient. In this case, the ingredient is CO2.
Okay.
So by letting this stay, you can see that it still remains green, close to the paper towel. So
Yes.
this is exactly where we want to conduct the chemical reaction. So you don't want to conduct the chemical reaction far away where it's limited CO2. By conducting the chemical reaction close to this region where now there's radiating CO2 in the solution, then this is where we show that now the efficiency of conversion to products
Right.
increases because there's more CO2 locally
Right.
close to it.
Right. That's very helpful. That's very helpful explanation. And also that I guess most of us don't realize it's really hard to capture this stuff. So that's a major thing. And thanks very much for that. Now, then, so you've come up with this very clever approach. And is there any difficulty with converting this to scale so that you can do it in large amounts and you're doing it, pulling it out of the atmosphere, presumably?
Yeah, and that's actually the challenge that you mentioned, that the CO2 that I showed in my experiment is 100% pure CO2. But in real life, as you know, in the atmosphere, there's 400 parts of CO2 for 1 million parts of air. So it
Yeah.
is very dilute. And,
Yes.
you can think of this as a grain of sugar in a 250 milliliter cup of water.
Yeah.
And now you have to design a system that would selectively take this sugar particle out. And this is where the engineering challenge comes, because you have so many other molecules in the air, but you want to selectively only capture the CO2. So that's where now addressing this challenge is very important, and this is something my current research interests and my group here in Vancouver at Simon Fraser University, we're very interested in this.
That's very interesting. And can it be done? I mean, in your mind, it is doable. The question is how to figure it out and to do it efficiently. Is that?
That's correct, and we're battling time because we
Yes.
have urgency, and that's where in my group we have a multidisciplinary approach because we
Yeah.
realize that this is not just a chemistry problem, not just a
Right.
fluid mechanics problem, not just a mechanical engineering problem. It's all of these coming together
Right.
and holistically finding a solution that can be scalable.
Right. And do you imagine it can be scalable? That I understand is a problem with all of these methods. So you get it worked out in the lab, but it's not something you can do a large scale, or it turns out to be so expensive that nobody will commit to it or something. Do you imagine this will be scalable in time?
That's a very interesting question, and that's where my current role. I'm very interested in fundamental research, but what I'm encouraging my students to do is, as they're doing this research in the lab, they are thinking about how this technology can be scaled out. What are the barriers? What kind of materials will be stable in real, operating industrial environment? And this is where this is the kind of training that I would like to provide my students, where we're looking at the overall picture. Now, plants do it. So, nature shows us how to do this. So I would want to think that if we got together and, looked at this from a multidisciplinary lens, that it is also possible to scale this up and to have a viable technology. And this is where support from multiple partners comes in,
Right.
which is, the private, especially in our academic environment,
Right.
engagement with the private sector, engagement with government and policymakers, and
Right.
leveraging funding opportunities that are provided to showcase how this can be translated quickly.
Right. Well, that leads directly to our last question. I wish we had more time for this. We're just about out of time, but you mentioned you have these people with different disciplines, and that this is one reason we want to come back to your lab later at another time because of this great interdisciplinary approach to these huge problems. And so could you tell us something about that? Your lab is established on that idea of interdisciplinary approaches.
Yeah, absolutely. And the name that you mentioned of my lab
Yes.
encapsulates that. So engineered interfaces essentially means that finding where bottlenecks to performance and longevity occur in sustainable energy systems. And we realize that a lot of these impediments occur at interfaces or boundaries. So by interfaces, as an example, the bubble interacting with a liquid,
Yeah.
there's a boundary between the bubble and the liquid. So now by engineering that, by using this sort of paper towel approach, we can have a significant enhancement in the performance and longevity of not just CO2 capture systems, but multiple energy systems. And a good example there is also solar panels. So typically solar panels, they're left out in the atmosphere and the
Mm.
operating environments, and there's dust accumulation that can occur, there's snow that can stick on the surface of the panel, and then this would impede how much sunlight would get into the solar panel. So this is where we're interested in designing interfacial engineering approaches where we design surfaces that do not allow dust to stick to them, so that way it's able to clean itself and enhance. And then this is where you can see that the performance can be enhanced if it is allowing more sunlight to go through. So that is the overall mission. And again, a particular focus on CO2 capture and conversion. And this is where being in this environment here at SFU in the School of Sustainable Energy Engineering, it is possible to have this interdisciplinary lens.
Yeah, that is really very interesting because it says, I mean, at the beginning of the Industrial Revolution, you could have an engineer work out something, a plan for something or other. But today, these problems are so complex that it seems as though, like in your lab, you're dealing with physics, chemistry, engineering, a host of things. And then you have to interface on top of that with politics and academics and all sorts of things. So you have to be complex at the start to be successful. This is most interesting. Again, I hope we can come back to your lab and watch you solve a problem in this manner in the early part of next year, because it's it's indicative of a whole future, the way things are going to be done in the future. This is really great. But Dr. Khan, thank you ever so much for this excellent information today. And I certainly wish you all the best in your lab and in your own work there.
Thank you so much for this opportunity. It's always a pleasure to describe the research and highlight the urgency